Now that we know this, we want to calculate the pH of different solutions. And that's going to be important because if we're going to do biochemical reactions, we have to control the pH and we have to figure out how we're going to do that. And in order to get to buffers, I have to just review with you how we do this, okay? So, for two cases, for strong acids and bases. For strong acids and bases, life is easy, right? It's easy because, for example, we only need two equations. One of the equations that we need is the ion product of water. Which, of course, is simply that the concentration of protons times the concentration of hydroxide anions must equal 1 times 10 to the minus 14 molar squared. The second equation that we will need is a mass balance of protons. Sometimes called the proton condition. Remember that as long as I'm doing a reaction in H2O, this equation, the ion product of water, must be satisfied. So, for example, to give you and again, the reason we can get away with only two equations, as you'll see in a moment, is we're going to assume that there's complete dissociation. So let's take an example. We're going to dissolve 1 millimole of hydrochloric acid into 1 liter final volume of H2O. Okay, now this is super simple because you know that hydrochloric acid will dissociate essentially completely into a proton plus chloride anions, right? And so, if our initial concentration of hydrochloric acid is 10 to the minus 3 molar, most of it is going to dissociate completely. So, there are two ways that we can do this, okay? First, we take equation 1. So what we're going to do here is this is our initial state. And we want to solve for the concentration of protons in the final state. So let's just use our two equations. We know, first off, that the concentration of OH minus is simply equal to 1 times 10 to the minus 14 molar squared divided by the concentration of protons. That's our first equation. Okay? And then we know from our second equation that there are two sources of protons. We know that H2O must dissociate into a proton plus a OH minus. And we know that hydrochloric acid that we dissolved must dissociate into a proton plus Cl minus. Okay, and so therefore we can write that the concentration of protons must equal the concentration of chloride anions plus the concentration of hydroxide anions. I can simplify this in two ways. I can say here that the chloride concentration must equal about 0.001 molar, because after all, the hydrochloric acid is completely dissolved, right? And therefore, I can write that the proton concentration must equal 0.001 molar plus the concentration of OH minus. And if I wanted to, I could use this equation for OH minus so that what I would end up with, I could replace the concentration of OH minus with 1 times 10 to the minus 14 molar squared over the concentration of protons. And if I do that and I plug that in, then I'm going to have a quadratic equation in protons, right? And I could solve the quadratic. Okay. Or I could just make some reasonable assumptions. I can assume, for example, that since it's an acidic solution, right, if it's an acidic solution, then clearly you would agree that the concentration of OH minus is a lot less than 0.001 molar, right? So the concentration of hydroxide anions is a lot less than the concentration of chloride anions. So I can just neglect this, right? Okay. So I can therefore say, so the proton concentration, therefore, is going to be approximately equal in this case to the concentration of chloride anions, which is equal to 0.001 molar, right? And therefore, the pH is now 3. So the pH started out for H2O, started out at 7, and then after I added 1 millimolar of hydrochloric acid, it dropped to 3, and I had a change in pH of 4 units. Okay? Easy. Super easy, if I assume complete dissociation.